Hey guys, I think we're gonna get started.
Data center power delivery, a series stacked architecture.
So, our first speaker is Yizhe Zhang.
Yeah.
He is currently a master's student in the ECE department at the University of Illinois. He got his bachelor's degree in electrical engineering from Tsinghua University in China. And his research is on power electronics with a focus on high efficiency power delivery for data centers. So please.
Yeah, hello everyone. I'm Yizhe Zhang. So actually this presentation is a practice for my qualified exam. Yeah, so my presentation today will be a series stacked architecture for high efficiency data center power delivery. And my advisor is Professor Pilawa. So this is the outline. First, I will talk about the background. The first, I will talk about the data center energy consumption, and then about the conventional power delivery architecture. And next, I will talk about the motivation, which is we want to further improve the power delivery efficiency, and how we achieve that is we rethink about the power delivery architecture, and the architecture is the series stacked architecture with differential power processing. And next, I will talk about the advantages of one specific type of the series stack architecture. And finally, I will talk about my progress on my thesis research. So data centers. So what are data centers? Data centers are the buildings that host IT equipment, which are servers or storage, etc., to provide internet services or computing, etc. So this picture is a photo of the Google's data center. And actually, data center consume a lot of energy. They consume like 2% of total US electricity in 2014. And so what are servers? So this shows a server. Actually, servers are specialized computers. They are often more powerful and reliable than ordinary PCs. And they usually work 24/7. And they operate with 12 volts or 48 volts. So to deliver power so actually servers are the workhouse of the data centers. They consume most of the electricity. So to deliver the power to the servers, we need to convert the electricity from AC utility to low DC voltages of like 12 or 14 volts. So what are the conventional approaches for these delivery architectures? There are basically two types. First is AC power delivery architecture. So in this architecture, we use AC-DC converters to rectify the grid voltage and directly support the servers. And the other basic type is the DC power delivery architecture, where we have a central inverter, a central rectifier, and it regulates DC bus, which is usually like 380 volts. And then we have dedicated DC-DC converters to step down the voltages and then supply each server rack. For example, we step down to 48 volts or 12 volts. So no matter which architecture we think about, actually, we can see that the converters process the full power that the servers consume. So because of this direct coupling between the delivered power and the associated power loss, the system efficiency of this power delivery architecture is actually limited to the efficiency of individual power converters. So how can we get better than this? So actually, if you think about we want to step down the voltage, so can we just like stack up the multiple servers and connect them in series, so that we don't need to do any power conversion? In that case, the power delivery efficiency for this stage will be like 100%. So, so ideally, if all the servers the power they draw are equal, they can. This is okay. They will divide the voltages equally. So, so this is achievable. But actually, the servers they have their current may not necessarily be equal. So their voltages, if we connect them in this way, the voltages may not necessarily be balanced, so there may be trouble. So how we overcome this is we can connect DPP converters to the in between the servers to compensate for the current differences. So in this case, the servers can have balanced voltage, and since the converters only process the difference in the current between the servers, the power process is much smaller, and the loss is also much smaller. So the system level efficiency can be extremely high. So we look at this, and we saw that we can connect DPP converters to compensate for the differences between the servers in the current between the servers. But how do we actually achieve this? So one example is we can use isolated DC-DC converters here, and this is like the path where we compensate for the differences between the servers, between the current in the servers. And so let's think about a simple example. So for example, there are 4 servers in the stack, and they are consuming 8 amps, 8 amps, 10 amps, and 8 amps. So how do we use the different DPP converters to regulate the voltage? So suppose that we can control the string current to be also 8 amps. And then if we can control the DPP converters to deliver 0 amp, 0 amp, 2 amps, and 0 amps, then the stack can be balanced. So we can think about in the power process in this series stacked architecture. We are processing 2 amps times 12 volts, which is 24 watts. And if we assume that 5% of the output power is lost, then we lost 1.2 watts. And we can actually compare this to a conventional DC architecture. So if we just remove the series connection, what we get is just the conventional DC architecture, the DC bus stage. So, and for the same scenario, actually the converters are providing the full power. So the process power is 408 watts. And the loss is 20.4 watts. So if we calculate the efficiency for DPP, it is 99.7, whereas the efficiency for conventional architecture, it is 95.2. So we can see that theoretically, we can achieve extremely high system level efficiency. So actually, there are 3 types of DPP architecture. So there are 3 types. If we think about if we want to connect the servers in series, but we need, if we want to connect them in series, the current needs to be the same. So how do we use DPP converters to make their current the same? We can like do from a server to server basis and like shuffle the current around. So this is a server to server architecture. And also we can do like this is a server to bus architecture which I just showed. We can use a dedicated DC-DC converter for each server and compensate for the difference between the server current and the string current. And also there is another server to virtual bus architecture, which is like a modification from the server to bus architecture. So instead of connecting the primary side of the DC-DC converters to the bus, DC bus, we can connect it actually to a virtual bus, which can be a capacitor. And in this way, if the capacitor voltage is much lower than DC bus voltage, we can the primary side of the converter, we can rate it much lower than the DC bus voltage. So actually, the server-to-server architecture, it has been investigated by Andrew from our group, and the server-to-virtual bus architecture has been investigated by Enver. So it seems like these two architectures both have converters with very low voltage ratings. But up to now, no one has actually built a real server-to-bus architecture. For this one, the primary side has to be like rated to the bus voltage, which may be very high. So this may seem like a disadvantage for the server-to-bus architecture. And so we look at this, and we discover actually the server-to-bus architecture, it has its unique advantages. And these advantages are that the other two architectures doesn't have. So next I will talk about this. So first of all, you can achieve the minimum total process power in the DPP converters if we control the converters properly. Actually, for the other two, this optimal condition is not guaranteed for all scenarios. So let me explain this. So for example, the same scenario, the first servers are consuming 8 amp, 8 amp, 10 amp, and 8 amp. So actually, the string current is not strictly constrained. We can control it to be any value. And so, for example, in the previous slides, we set it to 8 amp, and then the DPP converters provide these numbers. And if we set it to like 8.5 amp, the converters can like output minus 0.5 amp, minus 0.5 amp, 1.5 amp, and minus 0.5 amp. And they're still balanced. So we can see that actually there are infinitely many solutions. We can control the string current to be any value. But the total process power is different. How to calculate the total process power is we sum up the absolute value of the DPP converter output currents and time them by 12. So we can see that in these two scenarios, in the first scenario, the process power is 24 watts. And in the second scenario, where the string current is 8.5 amp, the process power is 36 watts. So actually, the first scenario is the optimal one. And if we can control the string current to be the optimal one, we can guarantee that the DPP converters process the minimum power. And actually, in the second scenario, I picked the string current to be 8.5. I picked that on purpose. That is the average of the 4 server currents. And actually, that corresponds to the server to virtual bus architecture. In that architecture, the primary side of the converters are connected to a capacitor. So that requires the DPP converters, their output current if we sum them up, they should be 0. So that requires the string current to be the average of the 4 servers. And actually, so we see that so scenario 2 corresponds to the server to virtual bus case, and scenario 1 corresponds to the server to bus case. So it means that for this architecture, we can control the string current so that we can achieve the optimal situation. And another advantage for the server to bus architecture is it has high reliability. What it means, first of all, it has redundancy, which the other two architectures doesn't have. So for example, the same scenario, and the string current we set it to be optimal. And what if one of the converter fails? We can control the string current to be another value. We can control it to be the current of the failed server, and control the other DPP converters to compensate for the other servers, and still the system is running, and we can supply to all the servers. And this cannot be achieved by the server-to-server architecture or the server-to-virtual bus architecture. And another point is actually, Emre and Andrew has done reliability analysis, where they quantitatively analyzed the server-to-bus architecture with conventional architecture. So in the first glance, we think that the conventional architecture should have much higher reliability. But if we think more, in the DPP architecture, the converters actually process less power. So that results in a potentially longer life for the converters. So if we take that into consideration, the server-to-bus DPP architecture, it has comparable reliability to conventional architectures, actually. Yeah. So that is the motivation why we want to do server-to-bus DPP architecture. So, this is the following are the progress on this project. So the hardware testbed, we build dual-octave bridge converters as the DPP converters. For the series stack architecture, especially the server-to-bus architecture, we need isolated converters and also bidirectional converters. And so actually the first square, red square, is the converter part, and we don't need to worry about the other two squares. And so actually, if we look at this converter, it is connected by a AC link, and on the primary side and secondary side, there are two bridges. So we call them dual-octave bridge converter. So they are symmetrical, so we choose them, and they are quite easy to control. So, and this is the hardware we built. And for the servers, we use the Dell servers, and this is the hardware testbed we built. We use 4 Dell servers and use 4 DPP converters and connect them in series. So the orange one is a series connection, and these are current sensor boards and microcontroller board. And we have also done some experiment tests. So in this test, we have like 5 intervals. In each interval, we control the servers to have some different test conditions. For example, in the first period, they all have high current consumption, and in the second one, 3 of them has low current consumption. 1 of them has high current consumption, which corresponds to the unbalanced case of the servers. But we can see that in their voltage, we can always regulate them pretty well, and the servers are working properly. And what we do with the control is a bidirectional hysteresis control. And this control method we inherit from Enver's work on server to virtual bus architecture. And so actually this one, we focus on the voltage regulation, and currently this one doesn't guarantee the optimal string current. But this is the entire experiment is the first demonstration of the server to bus architecture, and so the optimal current control is for future work. And what are the efficiency results? So we can see that these are the efficiency numbers, and for the first interval where the server currents are very balanced, we can achieve 99.2 efficiency, which is really high. And this is actually measured, not theoretical analysis. So finally, to conclude my presentation, first the background. I presented the background for thesis, my thesis project. Data center consume very large amount of electric energy, and conventional architecture, power delivery architectures are limited in their energy efficiency. And series stacked architecture with differential power processing can significantly increase the power delivery efficiency. And there are actually 3 basic types, and the server to bus DPP architecture has its unique advantages compared to the other 2 architectures. And my progress on my thesis research is that so the hardware testbed of the server to bus DPP architecture is built, and the experiment results currently show that the server voltages can be well regulated, and currently we achieve 99.2 efficiency. Yeah, so that's all of my presentation. Thank you very much. Yes.
I have a few questions. The first one, go back to the efficiency calculation, the first few slides.
Okay.
The number 4 and 5. This one? No, the calculation. Traditional PC's architecture and for.
Okay.
Oh yes, this one. Yes. So one thing is that I think you ignored the 8 amp conversion from the V bus to the main 8 amp out of the V bus. That conversion efficiency is not included in your first efficiency calculation, whereas your second one, that 8 amp is actually calculated. So I think there's a lot of loss isn't considered in your first case.
So you mean the V bus?
Yeah, like the 8 amp out of V bus, there's a lot of conversion loss over there.
Yeah, but for the second one, there is also like.
Right. For the second one, 8 amp is all included in your ECD converter. But the first one, the 8 amp, the main 8 amp coming out from the V bus, that conversion.
I would say that the current coming out of the V bus for the 2 architectures are similar, because if you look at this entire system, what is actually consuming power are the servers. The DC converters it actually just process the power, and it only consumes a little amount, which is their loss, and the back power it is still consumed by the servers. So if we look at the 2 architectures, what is delivered out of the DC bus are basically approximately just the 4 server power, which are both 408 watts approximately. So so that conversion power is equal, basically equal for these 2 architectures.
But the first one, your power loss is only considered those 4 DC converters, but not from the V bus.
The The second one, I also just consider the 4 differential converters.
I think it just the first one is some DC parallel.
I think it is already considered. Yeah. Yeah.
Can you go back to the slide where you have the several failures?
Okay.
So what do you mean by is it like a open failure or short failure?
Open.
How does the converter react?
So I was referring to open failure.
Okay, but what if it's
Well, then, yeah, then I guess I guess this architecture cannot regulate, and I guess the other architecture cannot regulate either. Yeah. So it means that like this top side of this server is directly connected to like VBus, which is 48 volts. Then I guess protection will trigger. Okay, over.
In your converter, if it is shorted, that you can do the mechanism so that the converter isolates itself. Right. You can do that on it. Yes, if the converter is shorted, yes, that's correct. What you say is correct. I mean, this architecture adopts, it's adopted, and you can do the protection. You can put some sort of isolation circuit around the DPP number 3. If it is shorted, you can detect it, and you can isolate it. Then it's not shorted. Another thing what you can do, if it is shorted, and if all DPP converters are rated high enough voltages, you can still, so let's say, give us this 48. If one of them fails, you can still regulate the remaining feed to 16 volts. If the converters and services are rated for that voltage, you can still level the power. So those are different options that just came into my mind. You can do, but at this level, I don't think that's right.
Yes.
Two comments.
Okay.
One is the previous slide, the optimal thing. Yeah. You want to do a zero-bit cost function approach for this optimal solution, like do a little bit to prove why this scenario is optimal versus the other. I don't think that's hard to prove, but to make a more generic function, cost function, that'd be great. More theoretical.
Actually, we have already like got the results. Got the results. What is optimal? Yeah.
But I mean, just for a function like terms of algebra.
Yeah. Okay.
Another thing is you cited the newspaper.
Uh-huh.
But you didn't mention much how yours is.
Okay. So I guess he doesn't build a very. He doesn't do much experimental on work on server-to-bus architecture. I did read his thesis on differential power processing, and he did a lot of analysis, and mostly they're about solar photovoltaic or ICs delivery for like CPUs, and for servers, I think he didn't do especially. At least for experimental work, he didn't do much server-to-bus DPP. Yeah.
Thanks, Yizhe.
direct line to the NSA. What's the optimal placement for this slide?
Optimal placement is right here. I'll just stand there and hold it for you.
Yeah, perfect.
I'm going to introduce our second speaker while people are getting some food. Don't get our second speaker is Matt Fedderson. He received his Bachelor of Science in Computer Engineering from the University of Illinois, Urbana-Champaign, in 2015. He is currently pursuing a Master's of Science degree in Electrical Engineering with a focus on the design of high-power dense machines for electrified transportation. In his spare time, he enjoys reading, playing games, making projects, and learning foreign languages.
Do I take that, or do I just speak here? We're good? Alrighty. Whoa. I'm back. All right. Hello, everyone. Now for something completely different. So I'm going to try and squeeze as much as I can in these 20, 25 minutes, but it involves a little bit of a lesson on superconductors and how they work, how AC loss works with superconductors. And then I'm going to talk about my research in applying these superconductor and AC loss theories to an electric machine design. So let's get going. In terms of motivating why superconductors can be used in electric machines, there's a big push for transportation electrification, especially in aircraft. So you've got the more electric aircraft, Boeing 787, the NASA NX-3 concept, where they tried to do a superconducting design in there. And since superconductors can replace the field and or armature windings with much higher current densities, you can get a lot higher torque, a lot larger power for the same size. So more power, less weight. It's a little bit of a enabling part of putting this into an aircraft. In terms of superconductivity as a concept, it is basically that a material will have zero electrical resistance for DC applications when it's below a certain temperature. So this is actually a graph of the very first superconducting element that was discovered in 1911, mercury. The guy took it down to 4.2 Kelvin, and below that he measured effectively zero resistance. And they have measured coils of superconducting material carrying current that does not decay measurably over the period of a year. They've measured it to be maybe 10 to the 5th years as some sort of decay constant. So you can basically call this zero resistance in DC conditions. Other factors may cause loss and may cause degradation, but in its purest sense, it's zero. Cryogenic temperatures, that's important. Apart from cryogenic temperatures, there's also a couple other operating parameters that limit your performance. So one of them is, so we'll start there, T, that's the temperature. B, that's the applied magnetic field. So if your applied magnetic field is too large, then you're going to lose your superconductivity. The third one there is J, the current density. How much are you trying to push through this material? And the final one is strain. That's stress or is it strain? Reed?
That's strain.
That's strain, thank you. Not a mechie. You can kind of put these together, figure out what your limiting properties are for each section, and form what's known as a critical surface. So here we have niobium 310, a very common superconductor, operates around 4 Kelvin. And here you have its critical surface. So if you take the magnetic field too large, you're going to come outside of this critical surface, you're no longer going to be superconducting. If you bring this to a higher temperature, you have an entirely different critical surface, right? We've reduced our operating range by increasing the temperature. And for this reason, people tend to bring superconductors to low temperature. That's where they operate. But it's very difficult to maintain that temperature. You'd love to have something a little higher. 77 Kelvin is really nice. That's where a lot of high temperature superconductors are trying to operate. But 4 Kelvin is still pretty common for a lot of applications today. All right. Another interesting property about superconductors, apart from their zero DC resistance, is the Meissner effect, which means that they will completely expel any magnetic field inside of them. What we're picturing there is magnetic levitation. So as a essentially perfect diamagnet, it will completely expel any magnetic field inside of it by producing screening currents. So as soon as there is some changing magnetic field around the superconductor, it will quickly, immediately, accommodate that with the magnetic, with the electric field inside of it. For large B fields, this kind of breaks down. The B field does, in fact, penetrate the entire thing if it's large enough. But if it's small, like for the case of this, N50 magnet underneath the superconductor, it'll do just fine. So when we're actually dealing with superconductors in an engineering sense, we care about a couple parameters that are different from the physics sense. So in physics, they tend to deal with bulk superconductors. That means it is a pure block of superconductor material. But in an engineering application, you're going to look at some sort of mixture of superconductor and non-superconducting material. Over here, we have pictured magnesium diboride. That's the little black parts inside of the copper. And basically what the copper does is it acts like a stabilizer. So as a whole, we can consider this entire thing to have a critical current density that we should be operating at or stay below. It has an operating temperature, something you want to stay below or maintain. And then it has other parameters like the diameter of the wire, the fraction of superconductor within the wire, an N value, basically the slope of the transition between states, twist pitch, number of filaments, the material, and so on and so forth. There's a lot of things that you can worry about when it comes to these sorts of materials, but these are more or less the ones that I paid attention to in my study. Okay. Moving into AC loss. So I mentioned that there's no DC loss for superconductors, and that's really fine and dandy. But when you try and push AC magnetic field through a superconductor or AC current, you get interesting effects. So AC field, that screening effect that I was talking about, the Meissner effect to try and dispel the field, the currents are represented by these red and blue shaded areas. So the theory says that the red area, we'll call it as full critical current density, and the blue is the negative of that. So you're essentially going to get your right-hand rule expelling the magnetic field from the middle of the material. But if you have too much magnetic field, all of it penetrates. The superconductor is still trying to expel it, still trying to generate screening currents, right? And the entire bulk of the material is now saturated with current, going one direction and going in the other. The net average across the entire area is 0, but it still has some moving within it, right? So when you go back and forth, you magnetize the material, you give it some current, you move backwards, you magnetize the material the other way, you move the current the other way. You're moving against these magnetic moments. This is a hysteresis loss given by that integral over there. Very similar to iron, just on a much larger scale. And we have a picture of a B and a magnetization plot. Should be very familiar to all of you, but a lot of this boils down to the fraction between our applied field and the superconducting properties themselves. So the superconductor can only take so much before it saturates, right? That's our B sub P. They call it the penetration field. Depending on how much we're trying to push through that, whether it's below or above it, we get different values of our hysteresis loss, and those are written right there. In the applications that I'm going to be talking about later, which is the motor, a lot of this is in the second category for beta greater than 1. That means we are absolutely saturating material, we are giving it a lot of magnetic field, and we are saturating the tiny bits of superconductor in there. Another thing is if we have AC current. So AC current gives a similar thing. The entire current magnitude going through the material can be expressed as the critical current occupying some space. If I go all the way to the critical current, then I'm going to fully saturate the material with current. That's right up there. And as I come back, I start giving it some negative current density to compensate. So even though I started at 0 amps up here, I ramped up to full, and I started to ramp down. My current distribution at that point is a combination of positive and negative currents within the material. And this is an unintuitive thing to try and grasp because in copper you just don't have that kind of interaction. But in superconductors, it tries to maintain the state that it's in, and there's a large hysteresis component, or rather there's a large history-based component to what its current state is. So if it reached a fully saturating point in the past, then there's going to be some distribution of current such that it is still fully saturated now. Kind of a simplified explanation, but this is how superconductors kind of operate here. Based on this model, there has been a very famous equation describing the loss, and that's again as a fraction of the current you're applying and the critical current or saturation current that it can handle. So that's this I parameter here. I is the fraction of the current you're applying and the total current. This is called the Norris equation and is very commonly used to approximate loss in very low current applications. What if you have both, AC current, AC field. The science here is a little fuzzy. A lot of it is experimental data that has shown that depending on the magnitude of current and depending on the magnitude of field, you're going to get some multiplier. So over here we can see a quick graph that shows, okay, if we have 1/10 of our saturation field, and we have, say, 1/10 of our saturation current, then we're going to take, let's see, which one are we looking at? We're going to take our saturation field loss equation and multiply it by a factor of 4. There's a similar graph that compares the saturation current equation with a similar multiple, but it essentially says if you take one of these previous, so if you take this equation, or if you take this equation, doesn't matter which one, you can find some multiplication constant based on the other parameter that you're also applying. Okay? A lot of this is based on engineering and experimental applications, things that they just measured and found some sort of approximation for. And finally, still getting through the intro, finally there's a coupling loss. So as I said, real superconductors are combinations of a normal component like copper, and inside of that component you have actual superconducting bits. So here we can have a circular copper cross-section, and those tiny little bits inside are little filaments of superconductors. Or you can have tapes up at the top. That's also very common, especially for high temperature. These tiny little superconducting components are very likely to be magnetically coupled to each other. So down here you can see an instance where none of them are coupled, so all the current flows within the superconducting points only, whereas over here you have coupling between the filaments, so you can get cross currents that cut maybe through your copper or nickel or whatever your material may be between the superconductors. There we go. So based on the twist pitch and the size of your filaments and the amount of filaments and the resistance of your material, all these things come together. You can determine there's essentially a inductive time constant to your coupling currents, and there is a general loss equation that you can come up with based on all of this. And this is all very much simplified. There are some other sort of out there effects, such as maybe this inner portion can be shielded based on the outer portions, but I'm not really going to cover that right now, kind of outside the scope of the work. These are basically the two biggest contributors to AC loss in superconductors, in practical superconductors. All right, something that looks like this. A lot of these equations have been validated in literature. They've been validated in experiments, especially for variations in current and variations in field at the same time. Once you get above the saturation field, your current variation doesn't actually matter that much. Beyond a certain point, you end up getting a linear increase. Hysteresis is linear with frequency, right? So this will just kind of increase. And then depending on the twist pitch, you can get a shielding effect that happens with your coupling currents, and so your loss dips after a certain point. Just some experimental validation. Now, let's put this in the context of a motor, of a machine. One thing that we can do right away is we can replace the, let's not reference this yet, we can replace the field windings, the DC magnetic part, with superconductors. And just from that alone, you can increase the Tesla that are being generated from, say, 1 Tesla up to 3 or 6 or 10, right? As long as you're within the operating parameters of your superconductor, you can increase this to a fairly large degree, and that'll increase the torque produced, it'll increase the power, etc., even while maintaining the armature as copper. So that's what this picture here is. This is a design that David came up with over the past 2 years, and it involves a stationary outer portion that produces DC field with superconductors, and a rotating inner portion, that's your 3-phase armature, and that's normally copper. So what I'm looking to do in this work, or what I was looking to do in this work, is to replace that copper armature with a superconducting armature component. So now we have both a superconducting field capable of producing very high fields and a superconducting armature component capable of pumping through a lot of current. So the things that we care about on this superconducting armature are the changing magnetic field B. That's our changing B field. Our transport current I. There's going to be some phase difference between them. And this is kind of bonus, but you are going to get rotating forces on the wire. It's not something I'm going to analyze in this work, but it is something that will be rather significant, especially at high speeds. So you remember me mentioning at the beginning, one of the 4 components that affect superconductivity is strain. Rotating forces are definitely going to give you some kind of strain. Magnetic components or magnetic effects in the wire, that's also strain. Not analyzed here, but also significant. The field windings, little to no loss, especially because the field windings are synchronous with the rotating armature field. So we're not going to worry about that for this as well. So what I developed for this was a method to analyze the B field across the armature. So you see I've highlighted it in green, one of the armature components, a cross-section of the bar, and how it changes over time. And then for each component of the B field here in space, I can assign it to a wire, take some wire parameters, calculate loss, and determine what is the loss of the entire machine based on this changing B field. And it was important to keep a lot of things constant to try and enable some measure of comparison across everything. So the field coil current, the DC field that I'm generating, is constant. And you'll notice in this design there's 2 field coils. So I'm writing 2 currents there, amp turns. The current density in the armature is constant. So for our partially superconducting design, the copper held about 7 to 10 amps per millimeter squared. Over here, we're trying to pump in 100 amps per millimeter squared because we can. This is superconducting wire that we're talking about. And finally, I wanted to keep the peak B field within the armature constant. And this is important. In the partially superconducting field design, we pushed up to 3 Tesla, 4 Tesla, and further. But because, I don't know if I wrote it, in both of these hysteresis and coupling losses, there is a square dependence on current, or I'm sorry, a square dependence on B field. So what we found is that if you increase the B field too much, it dominates your loss. And furthermore, if you increase your B field too much, you start to go outside of your critical zone, your critical surface. So we try to keep this below a certain point, 1.7 Tesla. And then we started varying certain things like the frequency, the slot depth, the pole count, and so forth. One final note is that when we were calculating the total loss, you have your hysteresis and your coupling component. Those are calculated per cycle, so for 1 AC cycle, and they're calculated per unit length for 1 meter. So in order to get the entire machine, I have to multiply by the frequency that we're operating at, the total length of wire that we have for 1 turn, or 1 pole rather, and then multiply by the pole count, that's the P. So what do we get when we change the slot depth? We had a picture up there showing a small slot depth and a large slot depth. So how much of the bar area do we have to work with? What's good about having a large slot depth is you have more of that J cross B torque generation. But what's bad is that now you have more area for that B field to penetrate your superconducting wire. And it turns out that the benefit that you get from the first part, increasing the area so you have more torque, is outweighed by the losses that you get by increasing that cross-sectional area for B field. And you can see that in this graph, we have increasing slot depth going up here. We have loss in kilowatts up here, and we're varying the frequency. And you'll notice that it's a somewhat power-dependent thing, right? As the frequency goes up, you have some exponent multiple of it, and that's fine in terms of what we know about AC loss. And down here, where it kind of approaches some constant, that would be your hysteresis constant, which would be about the same throughout all this. So armature AC losses increase with slot depth increasing. One thing that I want to point out is that if we go back here, go back one, it's easy to say like, all right, we just want to minimize the frequency. Just find some component that's really, really slow, really, really stationary, and we don't have to worry about loss. But then you have to worry about the actual length of the wire that you have. In a lot of applications for superconductors, you're limited by the length from your production facility or by the cost. A lot of facilities may only be able to make 500 meters of wire in a month, or, I don't know, 10 kilometers of wire in a year. And maybe all this wire might not even be quality throughout the entire thing, so you're limited by the worst aspect of the wire, right? The price tends to be very large as well. A lot of people are trying to bring this down to $10 per kiloamp meter, which is still pretty expensive for the applications. But this graph isn't necessarily an optimization of any sort. It's just to try and give a perspective on what area should you be looking at if you're trying to worry about length as well as loss. So if you are constrained, for instance, by your manufacturers, then there might be a line that you have to draw here and say, all right, I can't really operate below that point because my length gets too long, right? Same thing with cost. Some very basic things that we can surmise. For 8-pole machine, you have some section of loss based on your slot depth. I have this as cryogenic power. If I have loss at 20 Kelvin for a certain type of wire, I need 100 watts of cryogenic power to remove that 1 watt at 20 Kelvin. Does that make sense? So if I have 4 Kelvin that I'm operating at, and it generates a watt of heat, my room temperature cryocooler has to input a kilowatt. So the colder I'm operating at, the more energy I need to get rid of that heat. So at 20 Kelvin, which is what we're operating at, it's about a factor of 100. And then this translates to efficiency over here. 20 pole, loss efficiency, etc. Another thing that we varied is the pole count. And this is interesting in the sense that the poles, as a static number, will basically give you a factor increase on your loss, right? If I have loss at an 8-pole machine, I increase that to a 46-pole machine. It's basically a linear dependence. And you can see that from here, right? I have my 8, 16, 20, and 46-pole machine. These all have different radius as well. That's kind of an important note. These are all entirely different geometries in that regard. But the general trend is still the same. This does not take into account the length. Again, this is just loss. This is somewhat important when you start thinking about applications, especially for something that's like a 46-pole, 2-meter radius machine. That's something that's more likely going to be some sort of offshore wind, right? So 46 poles at 60 hertz, that's 150 RPM. I'm more likely going to be operating down here, right? My 10 RPM or less. That's probably 2, 3, 4 hertz. So we're working pretty well at that, especially if we're talking about, you know, the 10 megawatt range that this study is in. If we're looking at 8 poles at 60 hertz, we're at 900 RPM, and we're somewhere around here. That's okay, but that doesn't really have any useful purpose unless you're looking at maybe ship propulsion. So depending on your purpose and depending on what the application is, you might find that your loss is acceptable or not. So a quick conclusion based on all of this. First, I'd like to point out some comparisons to the previous work that we did on partially superconducting. There's still some work going into this, but just for a general trend, at 8 poles, our partially superconducting length was 157 millimeters as its active length, but the fully superconducting length was 200. And at 46 poles, a much larger machine, the partially superconducting length was huge, whereas the fully superconducting length is small. And this is something I'm still looking at, but the general trend is that the huge increase in current in our armature doesn't help much for a smaller machine, like a smaller sized machine radially. But it does for something that's much, much larger, around 2-meter radius. I don't want to draw too many conclusions from that, but it's an interesting data point to look at. In general, for a partially superconducting machine, it seems to be better for a low torque, high speed sort of a material, or I'm sorry, application, because your frequencies are low, the B fields are still high on the copper, which doesn't really matter, and you can still get really good power density out of it. For fully superconducting, it's still limited to smaller scale frequency areas, right? Wind, possibly ship propulsion, but not necessarily to air, which would need something like 8,000 RPM, 400 hertz, etc. In terms of AC loss, the industry is already working on things to mitigate this. So clearly, minimize frequency, wires and turns, field magnitude, of course. Cost and length, all right, that's where you start getting that trade-off, right? And then in terms of material, you can change the resistivity, the twist pitch, the critical current, filament count, et cetera, et cetera. These are all manufacturing challenges. And they are projected to improve over the next few years, but it is a challenge right now. In terms of future work, there's a huge need for experimental data on a lot of these loss equations. It's good to have them and to say that they're validated for the low area that they've been tested in, but for something that's greater than 1 Tesla or for 2 Tesla or higher, there's really not much data. And also for anything faster than 2 hertz, a lot of people don't really have much data either. So for that particular range, which would be really applicable for a motor, that kind of data is incredibly useful and incredibly important. Same thing, high field, low current. That seems to be one area that a lot of researchers are fairly averse to. They like the high current, low field application. MGB2, that's the wire we were talking about, projected to increase dramatically in performance over the next 10 years in terms of length, critical parameters, current, temperature, etc., and of reduced AC loss. There's also a trend to use other types of materials, YBCO and BSBISCO, they call it. Those are those 77 Kelvin types of materials. That's more of a liquid nitrogen temperature, and so clearly you're going to need less of a heat load in order to actually operate that. And in terms of the study that we have here, there is a clear need for an optimization on loss and cost, or loss and length, and an E&M study on optimizing the coil placement for optimal B field distribution over the coils. And I think that's it. Any questions?
Hello, thank you for that very nice presentation. I'm curious on slide 10. Compared to skin depth. When you talk about AC things, you're talking about skin depth. So
Right.
you compare, like, if I was wanting to size, like, wires for something I do, I think about skin depth as an additional thing, but you didn't talk about that at all.
Right, right.
Can you tell me how, if I wanted to go build a superconductor, which I'm now excited to go do, how would I size those strings?
It's kind of a complicated question to answer because this particular theory is for pure superconductor. If I were to take my MGB2 and roll it out into a wire without any copper or anything around it, then I could use this.
Okay.
If I'm looking more towards the actual application, like I think there was something like that, then I have to do it on a per filament basis and try and find some approximation for that. So it's not necessarily a skin depth thing as it is just a property within the superconductor itself. If you're going to try and size it, you'd worry about the critical current because each of these shaded components is critical current going through it. And you'd worry about the size of it, right?
Just a quick comment on that. So skin depth, we have resistivity in your formula. The resistivity of superconductor is like at 0. So if you compute skin depth, you get 0. So this phenomena is analogous to skin depth, but I think this penetration depth has to do with how does, depending on the field, how much of the conductor carries critical current.
Yeah.
Yeah, that's why I asked, because it's starting to look analogous. So I didn't know if it was,
Yeah, somewhat. Yeah.
it was like a parallel.
And a little bit more on that resistivity thing. When the material is trying to completely expel any B field, it happens immediately, right? There's no resistivity. But when we talk about the coupling loss, because there is a resistive material between all of the superconductors, we can give some sort of inductive approximation of the system based on an average resistivity. But, yes?
So another question. You made like the amazing like alarm bell ringing comment like a few slides later.
Sure.
Where you're talking about the torque and the B field.
Sure.
Maybe 20 almost. Maybe 2 more slides. Maybe, yeah, it was this slide 19.
Sure.
So I'm curious, have you thought about plotting that in some way versus like the actual per unit area? Like I'm thinking if I want to extract the heat, I want heat flux. So that's watts per centimeter squared.
Okay.
So you can see, I can maybe see that straight off in terms of area. Have you thought about that at all?
No, I haven't, but that seems...
I care about torque and I care about B field.
Yeah,
Maybe
yeah.
see some...
No, that sounds like a very good idea. I haven't thought about that.
So how do you pull the heat out?
There's a couple different methods. In this particular application with the rotating armature, that's one of those things where I'll say, oh, it's a later problem to solve. But for something existing, like say in the field, right? The field is stationary, and that's something that we've already worked on. You can do a variety of things. There are existing external refrigeration systems that can pump coolant through there. You can do a conduction cooled method with a really long heat path. Vacuum sealed, of course, but there are ways. Difficult ways, but there are ways. It's one of the main challenges in terms of transitioning from a regular, more traditional machine to something that's based on superconductors. But.
And then the 7. Oh, maybe someone else has a question. All right, maybe not. So that 7.5 Tesla is a massive field. That's absolutely amazing.
Right.
So is that why you guys are working on that extra external coil to dampen that out?
Yeah. So was it somewhere around here? Yeah. So you have your main field coil here. So current going in here, current coming out here. You get your net field. And then we have our opposing field current going out there in there. And so the net outside is going to be reduced while you're still keeping a very large margin in there. Yeah. And that was one of the main reasons for sticking with this design, because it solves that problem of the external field. Mm-hmm. All right. Do you have a quick question? Question?
So you said you're lessening the heat load in your conclusions? You said something. One more. Sorry, forward, 24. Yeah, okay, you said that we would be able to lessen the heat load. I don't remember what you were talking about.
Where is that?
So then how are you lessening the heat load?
On what?
On the machine level. You said that you were lessening the heat load on the machine level? It sounded like? Maybe not.
Maybe not? I don't know.
Okay, you said we typically operate at 4 Kelvin, right?
A lot of current designs for MRI specifically will operate at 4 Kelvin.
Okay, do you know why specifically 4 Kelvin?
Liquid helium evaporates at 4.2 Kelvin. And so they'll just immerse the entire thing in liquid helium and then use some sort of refrigeration loop to keep it at that.
Okay.
And that's the same thing, same reason for numbers like 77, that's liquid nitrogen. But you can still operate anywhere in between that if you have the right cooling equipment.
So, but then you said that you were optimizing this for 20 Kelvin?
Yes.
Okay, so then why were you having that difference?
A lot of that was due to the choice of the superconductor that I had. So niobium-310 is one of the more common ones at 4 Kelvin, but you can't. The heat load at 4 Kelvin is enormous compared to any heat load that you'd have at 20 Kelvin. Niobium-310 can't go above 14. So I would need to choose something else. Basically, for any AC application, I can't operate below 20 unless I want some massive load on my cryogenic system.
Okay, so you're saying that the amount of energy created at 4 Kelvin.
Maybe it's the same. Maybe it's the same loss, right? But if it's loss at 4 Kelvin versus loss at 20 Kelvin, and it's the same amount, it's much easier to cool that 20 Kelvin version.
Okay, that makes sense.
Yeah.
Okay, so but then why did you pick 20 Kelvin? I understand like from the loss perspective.
So liquid hydrogen, liquid hydrogen evaporates at 20 Kelvin, yeah. And that's one of the proposed fuels for some types of aircraft systems or in space as well.
Okay.
All right. Yes.
I'm a bit confused.
Sure.
You showed a curve where you said the thing was 1.7 Tesla.
Sure. Yes.
And then you are saying you are raising the flux density to 10 Tesla.
Okay. Yeah. Sorry for the confusion. There's a distinction between the partially superconducting design that we had in the past, and that was up to 10 Tesla theoretically, right? We would operate more in the middle of that range. For something like this, the fully superconducting design, we couldn't really do that because the higher your B field is, the more your AC loss. Because the partially superconducting design didn't have that kind of issue. So we could push the Tesla up. So it's kind of two different parameters and two completely different situations. Yeah. Yeah. Okay. All right. Thank you.